So far in this unit of astrophysics, we've really been focusing on quantifying and calculating different properties of stars, whether it's temperature, radius, brightness, luminosity, or distance, how we find or measure that distance. We've really been looking at ways to make these properties numerical. Today's conversation is much more about the storytelling of what a star's lifespan looks like. It's not necessarily rooted in numbers. There will be some numbers along the way, but we want to know, what is the typical story of a star? Uh, how does that show up? And for our star, the sun in the middle of our solar system, what is its future going to be? Today, our focus is the evolution of stars. Now, if you wanted to study something here on Earth, say you're a biologist, and you wanted to figure out what the lifespan of a certain lizard is, or even the lifespan of a plant, you would basically watch it throughout its entire life and figure out, okay, for this particular sample, this is what's happening as it ages. And we can do that because of the human lifespan is longer or long enough that we can see measurements over time and see how that thing is aging. Now, we can't do that same thing with stars because stars have a much, much longer lifespan. The scale that we're talking about is many, many billions of years. That is not something that humans are going to be able to watch in some useful way as it's aging. So instead, we're going to have to use some different techniques. Now, imagine that you were an alien that came to Earth, and you were trying to figure out what does a human lifespan look like? As humans age, how do they look? What sorts of properties would they have? Now, you wouldn't necessarily have to follow one particular human over time to do that. Instead, all you have to do is really take a subset of humans. Take a picture and look in that group. You'll see some humans that have some patterns, maybe graying hair, more wrinkly skin, um, and you have some humans that are shorter, kind of look a little bit different, look smaller versions. And from that, you can actually figure out that there are some patterns here that might contribute to just the life cycle, how a human ages. Same thing is true with stars. We can look up at our night sky and see many different stars at different points in their lifespan. So even though we haven't really been able to watch one star age, we have a pretty good idea of how it happens because we have so many different samples to choose from. We can take those samples and figure out, all right, these are the different parts of that life cycle, and this is where we think it is headed. We talked about HR diagrams in the last lesson. Here's another great example of an HR diagram. It is obviously not in English, but the pictures kind of tell the story, that these pictures of stars aren't necessarily what a star looks like, but it's a representation in cartoon human form of basically that life cycle. So today we're going to be talking a little bit more about that. Now, different stars have different lifespans. Not every star is going to uh, be around for the same amount of time. And it has to do with how fast they are burning their fuel. This picture is a little bit small, so it might be hard to see. But along this main sequence, we see that you increase the lifespan of a star as you're going down that main sequence. And when I say down, we're going down in luminosity, but we're also going down in temperature because, as you remember, the temperature scale decreases going to the right. That means that over here, these red dwarfs are going to have the longest lifespan. The reason for that isn't because they are more powerful than these other ones. It's actually the opposite. Those red dwarfs have a longer lifespan because hotter stars burn their fuel more quickly and then they die faster. So these hotter blue stars, bigger, they burn through their fuel very, very quickly. It's still long lifespan, 10 billion years or so, or 10 million years or so. But these red dwarfs, since it's kind of a slower burn, will stick around much, much longer. So it's important to know with stars that as they are kind of in their standard normal state, they are under equilibrium. Equilibrium in the case of a star basically means that as it has a high temperature, that temperature increases the pressure. Those molecules are moving around faster, just like you would with any gas, and it causes expansion. So if it gets hotter, it's going to start expanding. But it also has some limit there as well, because there is a ton of gravity pulling back inward for these stars. So all stars have kind of these competing forces. They have the pressure out and the gravity in. Stellar equilibrium is when those competing forces perfectly cancel each other out. If something happens to the star to make it burn hotter, it is going to grow a little bit because the temperature is increasing the pressure, and it will find a new equilibrium state at a larger radius. So another example of that here. Energy pushes out, gravity pulls in. So as stars age, there are a variety of different things that happen. Um, all stars kind of start in this simplest form of fusion where they are fusing hydrogen into helium. Our star, the sun, is currently undergoing this stage. So what's happening is inside there is this helium core that's happening because the hydrogen is turning into that. It's basically a helium factory, if you will. Um, as this is happening, that fusion is creating energy. It's causing the star to heat up. And it's still much, much easier to fuse hydrogen together than it is to fuse heliums together. So as it heats up, the hydrogen part is going to expand, and eventually that helium, if it gets hot enough, will start to fuse as well. Helium can fuse into carbon. But for most stars, medium to small stars, that's about as far as it can go. Our sun is not going to fuse beyond carbon because it's just not going to be hot enough, not a powerful enough star to do that. So when it gets to this stage, we're going to see some kind of crazy things going on within that star. So our sun starts out about here on the HR diagram. And as it heats up and is burning through that hydrogen, it will get larger and larger. As it gets larger, its luminosity increases. But ironically, its temperature is actually going to go down because as it's getting bigger, it's spreading out its energy more, um, which is decreasing the surface temperature of that star. Eventually, it's going to burn through a lot of its hydrogen, and then it will undergo something called a helium flash. It'll shrink back down to a core again, and that helium will then be hot enough to start fusing itself, eventually forming a planetary nebula, and it blasts off that extra mass and then eventually is basically just a leftover core that we call a white dwarf. A great example of this is a website called Star in a Box. On this website, Star in a Box, we can actually see an animation of what's going on in the life cycle of this star. So I've got it right now set to a mass of one sun, a solar mass of one. So basically, we're going to watch what happens to our sun as it ages. So here you can see it is going to start by expanding very, very, very large, much, much larger than our sun currently is, becomes a red giant, and then expands again when it is going through its helium, and then eventually crashes and becomes a white dwarf. So let's get into more detail about our particular sun, because that's a star that we care a lot about here on Earth. Now, the life cycle of our sun looks something like this. So our sun it'll be approximately 12 billion years in total from its birth to the time that it becomes a white dwarf. Right now, we are at about 4.5 billion years as far as we can tell. So we are in kind of the main part of this star's cycle, that it is just this yellow star sitting on the main sequence. But eventually, it will go through its helium, go through its hydrogen, become very, very hot, expand, and become a red giant. And as you saw, eventually that red giant will blow off its extra mass, becoming a planetary nebula, just leaving behind the core that we call a white dwarf. So eventually, our sun will become very, very big. The red giant actually is so large that the Earth, where the Earth's current orbit is, the red giant would be pretty close to the size of that orbit. So it wouldn't just look bigger in our sky, it would be part of our sky. We are not going to have to worry about that. that is many billion years in our future. So white dwarfs are a pretty interesting star. As I mentioned before, white dwarfs are basically just the core of a star. These are very, very hot, but they are very, very small. So they still have a fairly high luminosity because they are so hot, even though their size is just a fraction of the size of our sun currently. So to become a white dwarf star, there is a certain limit as far as how big the star could be to begin with for it to become a white dwarf. This limit is known as the Chandrasekhar limit, and it basically says the maximum mass of a core that could become a white dwarf is about 1.4 solar masses. Now, this is the mass of just the core that's left over, and the core only makes about 1/3 of the star's mass. So really, if the star is 4 times the size of the sun or less, it will become a white dwarf. Otherwise, it will not form a white dwarf. Um, so if the star's total mass is less than 4 times the mass of our sun, it will become a white dwarf eventually. So let's look a little bit at the life cycle of a more massive star. So as I've mentioned a few times, our sun is not one of the largest stars in the night sky. It's actually pretty small compared to some of the stars that are out there. A more massive star is going to be more powerful as well. There's more fuel there, and it's going to be burning hotter. Now, because it's burning hotter, that fusion can go to higher and higher levels. So we're not stuck just fusing hydrogen into helium and then helium into carbon. You can keep going, carbon to neon, oxygen, silicon, and then iron core. Once you hit iron, you can no longer create fusion. You may remember that graph that we had talked about, the mass defect per nucleon. Iron shows up at the very top of that, which means it is not energy efficient to keep going beyond iron. So iron is where it leaves off. Now, there is a limit governing the life cycle of a massive star as well. This is called the Oppenheimer-Volkoff limit. And this is the mass of the neutron star uh, versus black hole. So if it is a more massive star, it really has two possible paths that it can go. It can become a neutron star or a black hole. And this limit kind of splits them up. If the overall mass of that star that's left over is less than 3 times the mass of our sun, but still larger than that white dwarf, uh, then it will become a neutron star. If it is larger than 3 times the mass of our sun as just a core, it will collapse into a black hole. And we can look at this in the star in a box simulation as well. All right, I've got this star in a box simulation set to a mass for the star 10 times the mass of our sun. So if I hit play, we can see what's going on to that mass of the star. It becomes a super red giant as well, and then fuses, but then eventually becomes a supernova, and then ultimately turns into a neutron star stage because its mass is less than that 3 times the mass of the sun. If I start with a larger star that's 40 times the mass of our sun, and go through that same thing, that helium core burns very, very quickly. And since the mass is larger than 3 times the mass of our sun, it becomes a black hole, goes to this final stage. We talked about black holes a little bit in that first lesson, talking about the scale of astrophysics, because there was a very famous picture of a black hole that was taken a few years ago. We're not going to get into too much detail about this. Black holes are fascinating objects. They are so dense that the gravity is warping space-time enough that light is bent to the point that it cannot escape the black hole. So you've probably heard of black holes like suck all light in. Well, it's kind of true, but a simplification of that story. Think of it as bending, warping space-time enough that the light that's trying to go past it spirals in and can't escape. Very similar to if you've been to the mall and done one of those coin or marble things that spirals into the center. It is so warped that it can't escape. So the overall life cycle of our star, we could go a couple different paths that fork a few different times. If the core is less than 1.4 times the mass of our sun, it will become a white dwarf. If it is greater than 3 times the mass, it becomes a black hole. And if it's somewhere in between, those two, it will end up as a neutron star.